Good afternoon, delegates and invitees. So now for this session, we have Professor Mahendra Singh, Professor of Civil Engineering at IIT Roorkee as a chair. He is working in the areas of landside analysis and mitigation, stability of soil and rock slopes, rock mechanics, strength and deformation behavior of jointed rocks and rock masses, tunnels and underground excavation. He has supervised 11 PhDs and 9 are working now. He has published more than 50 journal papers and investigator for several NDMA projects. And we welcome Professor Mahendra Singh. And next we have co-chair, Dr. Kaustu Chatterjee. He is assistant professor in the Department of Civil Engineering at IIT Roorkee since June 2016. He has done his MTech and PhD from IIT Bombay. He was a postdoctoral research scholar in Kyoto University, Japan. His research interests includes geotechnical earthquake engineering, soil dynamics, and liquefaction. He has authored more than 25 research papers in journals, and he has supervised 7 MTech students and currently supervising 5 research scholars for PhD. He is recipient of G.L. Leonard's Best PhD Thesis Award from IGS, John Carter Award from I.I.Sc MAG, Best PhD Thesis Award from IIT Bombay, and ISSMGE Foundation Grant, UK. We welcome Dr. Kaustu Chatterjee. So now I request chair and co-chair to take over and start the proceedings. Thank you.
Thank you, Professor Raghuveer, and welcome everybody, the participants and Professor Hazarika and delegates. So it's my pleasure, and we thank the organizers for giving this opportunity. So let us start the session, and as I see, there is one SOAP lecture and there are 5 papers. So all they are presenting, all the 5 papers are, they have given their consent?
Yeah. Yes. But they are yet to join. 2 of them are there. Others will be joining now. I will get them.
So yeah. I hope all 5 will present.
Yes.
Okay. Then we are keeping 30 minutes for this lecture.
Yes, SOP lecture 30 minutes plus 5 minutes discussion, and all other papers 8 minutes plus 2 minutes discussion.
Okay, that's already decided. So I think we can start, and I request my co-chair to kindly introduce the speaker and then invite him for the talk.
Thank you very much, Professor Singh, the chair of the session. So it gives me immense pleasure to introduce Professor Hemanta Hazarika, who will be giving the SOP lecture for this technical session. Okay. Professor Hazarika is a professor of Geo-Disaster Engineering at Kyushu University, Japan. His fields of specialization are geomechanics, earthquake disaster mitigation, and geo-environmental engineering. In recent years, he is developing technologies for climate change adaptation from the geotechnical perspectives at the urgent need of the society, and the research is focused on those. Developing research methodology which incorporates and combines these 2 important aspects that the present-day society is confronting, that is disaster mitigation and environmental protection, is one of the most important goals of his research group. His research areas include field survey and testing, model testing and the simulations, element testing of natural and recycled materials, characterization of those materials, developing disaster mitigation systems using drones, IoT, and artificial intelligence. Aim of his research is to make best prepared for the immediate and present dangers facing the global community through geo-disaster risk mitigation. So with this, I now give the stage to Professor Hazarika to start his special lecture. Thank you very much.
Okay, thank you, Dr. Chatterjee, for the nice introduction. Before I start, I'd like to thank the organizing committee of 7th International Conference on Recent Advances in Geotechnical, Earthquake Engineering, and Soil Dynamics for inviting me to deliver this lecture. This is the title is Forensic Evaluation of Long Distance Flow in Gently Sloped Ground during the 2018 Sulawesi earthquake in Indonesia. Before I start, I'd like to acknowledge my co-authors, Mr. Divesh is a PhD student under me right now. Dr. Kyota from University of Tokyo, Professor Okamura from Ehime University, my former PhD students, Dr. Pasha from Image Eye Consultant in Tokyo, and Dr. Nurdin from Tadulako University in Indonesia. Well, the long distance flow that I mentioned in my title is what is that long distance flow and why that happened in a very, very gentle slope, for example, of slope of gradient 1 to 3%. Okay, this is just an image of the flow slide that took place after the 2018 Sulawesi earthquake in Indonesia. I'll just play this video. You can see what is happening, what has happened after the earthquake. This whole, the ground, they flow like this. So you can see the original, the city was like that, the town, part of the city. And after the earthquake, due to some phenomena, the whole part is gone. So this is the topic of today's lecture. Okay, so before I go into the details of the investigation that we conducted in Palu, let me give you a brief introduction on the earthquake itself. Before that, I think many of you may not know where is Sulawesi. As you know, Indonesia is a country of many islands. Main islands are Sumatra, Java, Bali, and Kalimantan, and this Sulawesi in the eastern part. So this is another island, and the Palu is one of the biggest city in the island, and the earthquake epicenter was about 80 kilometers from this Palu city. And the flow slides took place in Palu city. The earthquake was of moment magnitude 7.5, and it took place in September 28 in the morning with a peak MMI intensity of about 8. And it was caused by the shallow tectonic activity of this Palu Koro fault. So it's a fault-induced earthquake. This is the north-south component of the acceleration recorded by the stations installed by JICA of Japan, and this is the east-west. As you can see, the acceleration itself, the peak ground acceleration is not that high. It's about 200 gals to 300 gal. And this right-hand side, you can see the spectral acceleration versus the period of vibration. And from here, you can see that the short period between 0.1 to 1 second components are predominant. So that means not many buildings are going to be destroyed or damaged by this kind of earthquake. And mostly it's a geotechnical damage. Let me share you a video taken by some local people there when the flow slide took place. So in fact, the person is moving in a car in the opposite direction of the flow. Okay, that you have to remember. So you can see how it is flowing. You can see the red house actually. It looks like flowing, but actually it's not. Because of the relative velocity, okay? Now you can see this electric poles here, which is moving, okay? This one. This is this actually what happened after the earthquake. This is not during the earthquake. Okay, so this kind of flow took place in 4 different areas in the Palu city. One is from top, it is Balarwa. This is the Palu Koro fault, and this is the Palu river. Actually, I'm sorry, there are some characters in Japanese. Then one is Balarwa, one is Petobo, one is Jonoge, and another one is Sibalaya. The size represents the magnitude of the flow area. So you can see that the topography of the area, this is Petobo, Jonoge, Sibalaya, and Balarwa, Palu Koro fault. There is another normal fault. This is the active fault, okay? There's another normal fault passing through this area. This is the Palu River, and it's mostly the alluvial fan, and there are mountains on both sides, both east and west banks of the flow areas. Okay. About this, I'll come back later. So after the this flow slides, so it's claimed about 1,700 lives. Total calamities of this earthquake, about including tsunami, which took place along the coastal area, about 2,100. Okay, so these landslides or the flow slides itself claimed more than 1,700 lives. So after that, the JICA, Japan International Cooperation Agency, formed an advisory team with Professor Ishihara, Kokusho, Yasuda, Tohata, Okamura, Kyoto, and myself. And we went to the site several times, and I'm going to talk about those investigations and results of those investigations. So from our university side, me, Dr. Manafi, and my Indonesian student, and Divesh, we joined, and from University of Tokyo, Dr. Kyota, and Professor Tohata, also from Ehime University, Professor Okamura. We conducted the survey in 3 different periods, in 2018, 2 times, and 2019 once. We wanted to go in 2020, but because of the COVID-19, we could not go. We targeted these Balarwa, Petobo, Jonoge, and Sibalaya, these 4 areas. Of course, along these coastal lines, there are tsunamis, not due to the earthquake, but due to the landslides along these coastal lines, and that created tsunami. So we basically did some drones survey and performed PDCPT, portable dynamic cone penetration test, and conducted trench survey and collected some disturbed and undisturbed soil samples. The purpose is to determine what is or what are. We still don't know, actually. That's why I put both is and are. The mechanism of such unprecedented long distance flow in such a gently sloped ground. Okay. Today, because of time, I'll just focus on two areas, Jonoge and Sivalayas, which Jonoge is located about 6.7 kilometers from this Palukoro fault, and Sivalaya is located about 3.6 kilometers. So let me talk about Jonoge first. This is the flow site area. This is before the flow site, before the earthquake. This is after the earthquake. Okay. This blue one, I'm sorry, still in Japanese. This is the water channel. So most of one of the peculiar characteristics of this flow site is that most of the flow site took place around that. 3 locations, they have a water channels on the top of the start of the flow. So it covers, in Jonoge, it's the largest one, covers about 3 kilometer length and 1 kilometer width area. And the slope is just 1%, is the most gentle among the 4 areas. And irrigation channel here is just above the flow site, which also got damaged. And the flow site caused the overflow of the river downstream here and caused flooding in the neighboring areas. These are some of the photos. As you can see, this is the unlined irrigation channel. They were badly damaged during the earthquake, and about 3 to 4 meters of depressions, subsidence of the soils in the area due to the flow. We also observed some huge sandballs in the part which were intact, which were not damaged during the flow slides. This is about 2 to 3 meters diameter sandballs. As you can see from here, it's a very, very flat area. It's not sloped ground. On the start of this flow, near the cliff, we could see some geology of the area. Here you can see top is silty clay, then sand, some silty clay, then gravelly sand, then silty clay. If I pick it up, these 4 layers, then I can say that top part is the low permeable layer. Then we have a sandy layer, then low permeable layer, and gravelly sand layer. Okay? So one of the probable mechanisms of this kind of flow may be due to the formation of water film. I'll explain to what is water film later. Okay, due to this existence of this kind of low permeable layer, which acts as a kind of capped layer to prevent the liquefied soil to go up and forms the water film. But liquefaction alone cannot explain this phenomenon, because normally we have a lateral flow due to liquefaction, but it can be up to few meters, not like few hundred meters or few kilometers like here in this case. These are the situations in Jonoge, as you have seen in the videos, the red house, which looked like moving. Actually, in fact, it did not move. As you can see, this is a red house, which did not move. You can see the foundation shape. Foundation here, the exposed one, about 70 centimeter. We don't know, maybe the below you have 2 to 3 meters good solid foundation. That's why probably it could not move. The flow side, the thickness would have been less than the thickness of the foundation. So this is the flow direction, and you can see dot of deposition around this area. We conducted some penetration test close to that. So the surrounding houses were swept by more than 300 meters. You can see this is the 400 meters. So most of the houses, they were moved during the flow sites. So we decided to conduct several dynamic cone penetration tests in both in the failed area as well as outside the flow area. So these 4 are inside the flow area. This one is outside the flow area. First, about the PDCPT1 is the outside one, then 2, 3, 4, 5. Okay, 4 is near that red house. So this is the result from the location PDCPT1, which is outside the flow area here near the cliff, and these are the elevation of the area. And you can see here that groundwater level was about 2.3 meter when you conducted the test. And you can see that below this, up to about 2 meter, this is the converted N values, this is the penetration depth. The N value is relatively high, but below that you can see a very weak layer. Okay. And top of that, there is a strong layer which acts as a cap layer. So there is a strong possibility of sliding on the top of this weak layer, which is below 2 meter. And let us compare the results at the outside the flow area and inside the flow area, which is about 494 meter apart, and with a average gradient of about 1.9% here. So one is outside, one is inside. So if you compare that, then this is outside one, which I already described. This is the inside one. That means this part is already gone, right? This part is flowed. So that means practically we are conducting the PDCPT from this ground surface. So if you compare this and this, they're almost exactly same. So that means, and below that, there's relatively steep ground. That means there is the continuity between the results of PDCPT at location 1 and location 2. So let me now move on to the another PDCPT location, which is close to a bridge, which is actually there's a river. It's almost dry that time. There's a dry season in Indonesia. This bridge is completely collapsed. There's just a road going there. Actually, whole road is gone. So we conducted some PDCPT tests there. This is the elevation, and also we conducted a PDCPT one near the red house, which was not moved, and one near this blue house, which was moved by about 300 meters. So near the red house and near the bridge, near the red house and away from the red house. Okay, so all this PDCPT conducted in those locations, they show that, except here, this is near the river shore. Of course, the N value is very less, but other than that, below about 4.5 to 5 meters, the N value is quite high. So again, we could confirm the existence of weak layers in all the 3 locations. And the soils were mostly silty sand. And after that, this is our second investigation, and on our third investigation, we also conducted further PDCPT in some other location. Our previous one is 1, 2, sorry, 3, 4, and 5. Okay, and we decided that we should also conduct some PDCPT along this line and some PDCPT along this line because there are a lot of deposition in this area. So yellow pins are the new PDCPT and the green ones are the old, which I already described. So here, if you compare the new one with the old ones, okay, like we named J07, J08, J0 means Jonobe, then we can see that along the orange line here, okay, the thickness of the weak layer varies between 2.5 meter to 3 meters below the ground surface, existing ground surface. Okay, and this might be due to presence of the residual soil because it was this whole area flowed, so there are some residual soil deposits, and we started from the existing ground surface. So initially, of course, this weak layer should always be there. So this is all mud flow deposit due to flow failures. Also, in another location along the green line, the thickness of this weak layer is increased by about 4 meters, whereas our previous survey showed that it is between about 2.5. So it's between 2.5 and 4 meters the weak layers exist where displacement because of the residual soil deposit. Okay, so displacements were limited in the upstream of the flow side. Okay. And we also got some data conducted by Indonesian researchers on resistivity of the resistivity-based analysis of in a particular location, which is about 1.3 kilometers from the water channel that I described before. This is the water channels. So they couldn't do any resistivity analysis here because of the construction activities. So, and we also conducted some PDCPT survey there, and we found that these are the results, and you can see that this red line, red areas, these are the resistivity in ohm. So this rock and weathered rock, the blue one, we could see the existence of Artesian aquifer, and some light blue, which represents the loose sandy sand and sandy gravel. And our PDCPT results also confirm the existence of the loose soil layer at the top, and also somewhere around 2 to 2.5 meter location. Okay. So these are some confirmation of the resistivity analysis and PDCPT results, which are showing similar trend. Okay. Also, we collected some samples from different layers, J1, J2, J3, and based on the grain size distribution curve, we can say that most of the salts they were collected are liquefiable, because these are the standards given by Port and Harbor Research Institute of Japan, and potentially liquefiable and most liquefiable. You can see that all the soil samples fall within these curves, and also they have very high fines content. So that means these higher fine contents make the soil very contractive and flowable on the contractive side of the steady state line. And that was the research conducted by Professor Kokusho in 2019. This I'll skip because of the time. Then coming to Sibalaya, another location. This is the Sibalaya before, and this is the after. You can see that this road is completely broken, not really broken, it's damaged and moved by about 300 meters. There's displacement of the road. more than 350 meters, in fact. And we conducted some trench survey. We dug about 1, 2, 3, 4, 5 trenches on both sides of the floor area, and also some PDCPT testing we conducted. This is the trench actually near the cliff. You can see here, if I focus on this area, the upper part is sandy gravel, then low permeable layer, then sandy gravel, then sandy layers within the about 5 meters from the top. So we could confirm the existence of a low permeable layer, which is sandwiched between the sandy layers. This is very common characteristics of most of the trenches. We also conducted the PDCPT test, and the PDCPT test was conducted actually right here. So this is the cliff. So practically these are deposited soil. So of course we could see very low converted N values. Then after that, below 1 meter, we could see probably we had caught some gravel. But our Ehime University group, they conducted similar PDCPT in somewhere near that, but somehow they could get different results. But ours, we could not proceed further because of the and because we encountered some gravel soil. And next, PDCPT, another one next to Trench 4. Our results and their results are almost similar. You can see less here between up to 2 meters. Then it is some gravelly layers, then again some sandy layers and things like that. So this is again sandy layers, low permeable layers, sandy gravel, and sandy layers. And outside the floor area, we conducted another PDCPT test here, and there again we saw that this is the N value is very high on the top. That's why it didn't fail. And below that, we found a very weak layer. And again, on Jonoge, we collected many samples, S1 to S5, and these are the ranges of the potentially liquefiable and most liquefiable soils. And you could see that some of them fall within these ranges, and the fine contents are very, very high, which means they're likely to liquefy and cause the flow. And from the trench, again, trench 3, we could see similar trend, gravelly sand, low permeable layer, gravelly sand, and sand. So always a low permeable layer sandwiched between the sandy layers. Similarly, in another trench, trench 4, we could see similar trend. Okay? Always a low permeable clay silt or some kind of low permeable layer exists. So what is or what are the mechanisms? Okay. First, we have to look at this geology of Sulawesi. Is in the central Sulawesi, where Petobo, Jonoge, Balaroa, and Sibala are located, consist mostly of quaternary sediments. That is another problem of that area. And also the topography. I'm sorry, some of them are in Japanese, but I'll explain to you. Here, you can see that this is Petobo, this is Jonoge, and Sibala. This is the Palu River, and this is the fault, approximate location of the fault. You can see there's some old alluvial fans there, and some new alluvial fans were formed with times. And most of those flow took place near the new alluvial fans. You can see it's Petobo here, Jonoge here. Okay. So this is one of the reasons probably why this area failed. Okay. And we also confirmed the presence of artesian aquifer and also low permeable cap layer, and liquefaction of the sand layer below those cap layers can be thought to have produced the fluidized flow. However, it is very difficult to explain such long distance flow from the viewpoint of liquefaction alone. So what we could confirm through this forensic investigation is that the flow occurred in a confined aquifer, and there are some traces of liquefaction outside the flow zones, and the gradients are very, very small, 1 to 4%. And the flow distance were few hundreds of meters to kilometers. And these are not possible to explain using lateral flow due to liquefaction. So what we can think of is that they're very special soil, some kind of phenomenon like quick clay might have taken place, and there are inclined layers within the geology and formation of water flames and existence of artesian wells. These are some of the hypotheses of long distance flow we in the JICA technical committee came up immediately after these disasters. We have this liquefaction here, then flow started to taking place, then also the artesian groundwater came up, destroyed the cap layer, and led to the flow of the large distance fluidized flow of these areas. There are many hypotheses, but I'm not going to deal with all the hypotheses, but definitely we found that the impermeable layer, existence of impermeable layer, and probable water film generation in the below these layers. This is one of the hypotheses brought by Professor Tohata. As I mentioned, there are a lot of alluvial fan deposits there. Groundwater were plenty there, and there is a clay cover here, and there are many water springs even before the earthquake in that area, and water pressure under cover were more than the hydrostatic water pressure, and during the earthquake, these clay layers were destroyed and led to this kind of fluidized flow. This is Professor Tohata's hypothesis, but we cannot still confirm. So also from water film point of view, we have many silty layers here. So we have sandy layers. So there is aquifer here before the earthquake, and during the earthquake, the liquefied layer could not break this cap layer, and they formed a water film. And in addition to that, the aquifer water came up and led to this kind of large distance flow. This is another hypothesis. So maybe there are multiple water flames which were formed below the clay layer due to liquefaction and leading to the loss of shear strength. So what is water flame is that we just did some one-dimensional column test. There's a clay layer here, sandy layer here, sandy layer here. We just gave an impact using this hammer, and you can see that there is clearly the water layer forms below this clay layer. You have to observe very carefully. Okay, I'll put this video. You can see there's a water film here. There's a clear formation of film of water here. Okay, so this is probably what happened in some areas of Nepal. Okay, actually, Professor Koksho did a lot of studies before that. He conducted some model tests on water film. You can see this clay layer, two double clay layers, the embankment here, one single clay layer, sloped ground. You can see here, you can see how the flow is taking place. Without this ground movement, this ground only move. Similarly here. can see only above this cap layer, the movement is taking place. So this is what is water film. So my final conclusion is that we still could not arrive at any definite conclusions because this is very complicated phenomenon. So we have to look at the structure of the soil, effect of the non-plastic fines in the sandy, liquefiable sandy layers, and effect of the large strain, because this after the flow, they're moving at a very faster velocity. So that is a large strain phenomenon. So we have to decouple it from the pure dynamic phenomena before, during the earthquake. Then structure of the decay layer, whether they're continuous or discontinuous, and the thickness of the cap layer, how thick they are, and effect of the potential head on the long distance flow, because that head is going to affect the long distance flow of the area. And we have to quantitatively evaluate such a long distance flow either through numerical simulation or through the model shaking table test. We conducted many shaking table tests. So far we haven't succeeded actually to simulate the condition. And of course we have to produce some hazard maps for such disaster in the future in those areas which are prone to earthquake. These are some of the publications me and my PhD students, Rohit, has published, and you can go through it. And I like to acknowledge different people from JICA and Indonesian Geotechnical Society, different universities within the Sulawesi Island, and some consulting people from Japan, and also students of different universities in Indonesia, along with Professor Shihara Kokusho, Professor Yasuda, and Professor Tohata, and Dr. Takaya from JICA for their support towards this research. Okay, these are our teams during the survey taken by drone, and thank you very much.
Thank you, Professor Hazarika. It was very interesting talk, interesting presentation, and there are so many aspects. The phenomena is very, very complicated, and the initial part, right from initial part where you discussed a lot of things about the penetration test, and then you showed those experiments, it gives a very good idea. So before I open the floor for questions, so just one thing, one question, or if this kind of the thing is there, means what are the mitigation measures? Is there any way means these kinds of the problems could be solved?
Yeah, good question. Actually, that was the problem with JICA. That was the main purpose of JICA. What is the mitigation measures to be adopted? But we still don't know the mechanism. So unless we don't know the reason, we cannot give any medicine, right? Just like a medical doctor. So that was still the problem actually. But one thing we can do is that area is where the groundwater level was very high. Okay, the existence of aquifer. Okay, there are a lot of aquifers, and easily you can pump water actually. So one of the mitigation measure that time we thought of is the pumping out the groundwater. Okay, to prevent further disaster in the future earthquake. Okay, that is one thing. Or put some drainage pipes to drain out the water during the earthquake. Okay, to dissipate the pore water pressure and prevent liquefaction. Yes. Yeah. As of now, we can think of only those. Yeah.
Okay, thank you. Professor Raghuveer, I don't have access to the question answer, but if there is any question answer, Costa, can you read your question?
Yeah.
There are no question answer or anything in the chat also.
Okay. Can I have one question, please?
Yes, sure.
Professor Hazarika, very interesting presentation and very interesting study. So is there any history of earthquakes earlier, and which season this took place? Any idea?
In that area, or somewhere outside outside Indonesia or somewhere in the world. I mean,
Okay.
in the Niigata earthquake also, where the phenomenon of liquefaction was first, I could say, invented. Okay, we could say invent or discover. I don't know. Liquefaction was there, of course, from any earthquake. Liquefaction takes place, but the research community started looking at the aspects of liquefaction only after Niigata earthquake. Okay, there are a lot of building damage. Even in Niigata earthquake, there were some long distance flow, but not like this. Okay? Not like of a few hundred kilometers.
Quite far.
This is 500 meters, 1 kilometer, 1.5 kilometers, quite far actually. In Niigata earthquake, about 100 to 200 meters, there are some flow. Okay, that was there. But so far, nowhere in the world we have seen such long distance fluidized flow. That too in a very, very gentle slope, is very 1 to 2%, maximum 3% of gradient. So yeah, we have no idea. Yeah.
Before actually finding out the mechanism behind this, I think it is urgent to find out any such localities are there in the similar place. So that is more important to find out and move the people from there.
Exactly. That's why I put in my last conclusions is hazard maps. Okay. So you have to find those potential area and create hazard maps for those areas. That's important. Yeah, you are right.
Thank you.
Thank you, Professor Hazarika. So,
thank you, Professor Singh.
Yeah. Thank you very much. Very interesting. So can we have 1 or 2 questions from the, what is the mechanism? They have to put it in chat box.
Yeah, they will put it in Q&A chat box. Only
so
then you had to read out. Yeah.
There is no question there.
There were no questions in the chat box though.
Okay. Anybody in the panelists, if they want, they can ask among the present.
Okay. If there is no question, thank you, Professor Hazarika.
Thank you very much. Thank you very much.
And thank you very much. And we appreciate.
Thank you. It was.
So let's go